Over the years, I've gotten a lot of good proofs from students and a lot of really crummy proofs from students. And so I'm making this video to try and give you an idea of what exactly it is I'm looking for, which is, in fact, what I think most people are looking for when they're trying to read a good proof or write a good proof. So let's use an example that we had. Maybe you did this back in high school algebra. Suppose they asked you to do some algebraic manipulation. They said, prove that these two equations are actually equal. So we'll get to our algebra proof in a minute, but to start out with, I want to talk to you a little bit more about this process. And I'm going to do that by talking about how lots of people solve mazes, certainly how I solve mazes. When you're given a puzzle like this maze, you usually have some instructions that say, find a path from this arrow over to this star over here, right? But if you're anything like me, you don't actually always figure it out by starting at the arrow and just going straight through until you get this to the star, right? I mean, if I were solving this puzzle and if it were a little more complicated, I might start with a pencil so I can mess up a little bit. And then, I'll draw a little bit from the front and I'll see where do I get to when I go from the back. And I'll add some more and maybe I get into a dead end, so I'll erase that and, try a different path and try something from the end. And it's great. Finally, the two lines match up and I have my path, right? And, usually we stop there, but if you want to show off that you have actually solved the problem, you've solved the maze, then what you really need to do is you need to get from the arrow to the star. And I actually got from the arrow to somewhere in the middle and from the star to the same place in the middle, right? And so what we need to do is we need to erase the line that we drew. We'll remember where it was because we apparently have wonderful memory. And we also have amazing animation, right? Be impressed. And then we can redraw that line again in ink, and we really will start at the arrow and go all the way over to the star. And again, you should be super impressed. I wasted way too much time on that animation. But anyway, you get the idea. We did some scratch work, then we cleaned it up and we redid it. So let's get back to our algebraic equality that we were trying to prove. And we're trying to prove this. Of course, we need some reasons to justify each step in the proof. And we're going to use these two axioms as our primary reasons in our proof, our primary justifications. The distributive property of multiplication over addition. So we have a times b plus c equals ab plus ac. And I actually split these out. I said if the a is in the front and you're multiplying by b plus c, that's called distributed 1. That's what we'll call it. If the c is at the back and you're pre-multiplying by a plus b, the quantity a plus b, then we'll call that distributive 2, just so we have a couple of interesting rules. And then I'm going to wave my hands a little bit. I'm a computer science professor, not a math professor. So I may say as a justification, I'm adding two integers together. And there's probably a mathier way to say that, but it's been a long time since I've written algebraic proofs. So give me some slack. So here's what we want to prove. And the first thing you need to do is get out some scrap paper, right? You are not going to do, you're not going to solve most of your proofs, most of the things that you want to prove straight out, top to bottom, beautiful, neat handwriting. You get everything absolutely right? It's just kind of like our maze. You need to start, what I did is I put the first equation on the left side of the paper and the second equation on the right side of the paper, and I'm going to just kind of start messing with the left equation and see if I get anywhere, right? Oh, look at that. If I, multiply this out and I use my distrib 1 rule, right, I can get this. And then I say, I don't want to mess with that anymore, so maybe I go over to the right and I say, well, what can I get here? That looks like a good place to do distrib 2. right? So I multiply it out and I get 6 times 5 is 30x plus 6 times 2 is 12, right? And then I say, oh, let's just keep going and see if I can make these sort of look the same, right? We're just trying to get to the middle of our maze in some sense. And oh, look, I can swap 30x and 8 here because addition is commutative, right? And then I'm just going to say 8 plus 12 equals 20 by addition. There's probably some fancy rule I could use, but, you know, c'est la vie. All right, and I look at this and I say, boy, I can't do much more with this. Maybe I'll go back to this side. And what can I do over here? Well, yeah, okay, how's about I swap the 10x and the 20 here because these are these are adding together too, so I can swap them because, again, addition is commutative. And then I'll just add the 10x to the 20x to get 30x, and I'm just going to say my reason is addition. And I guess I want to be really careful, so I will swap these guys again by my commutativity rule. And I say, oh, wow, look, they match. I'm done, right? And the answer is you are not done. This is just your scratch work. You still need to turn this into a real proof. Right now you have convinced yourself of the truth of this equality, but you want to convince others. And to do that, you need to do a little bit more work. Now, one of the things that I will often get is proofs that kind of look like this, not a proof. Another thing that some students will do is they will just put equal signs between each lines, or they'll put an equal up at the top here. You don't know they're equal till you've proven it, right? So we don't want to just write equal signs here. We need to kind of start again. And so what we're going to do is we are going to try and make it look like it was totally easy for us, right? Even if it wasn't. So what we're going to do is we're going to recognize that really, if we wanted to convince somebody of this who totally did not believe that these two things were equal, what we would have to do is we would have to kind of go through these steps in this order from top to bottom. And then we'd switch over to here because we're working from here now, and we move up to convince them until we get to the end, right? We start at one side, we end at the other. Or we could equally start on the right-hand side and go down and then go back up on the other. But we need to copy this stuff out. So here's what we had on the left side of the paper before. And what we need to do is turn it into something beautiful. So here's the start of something beautiful, right? Here's my proof that these two things are equal. So what do I do? Well, I start by writing the thing that's on the left-hand side of my equation. And I do my first step. Well, what does that equal? That equals, up here I said it equals 10x plus 20 plus 20x. So I said 10x plus 20 plus 20x. Why? Distributed 1. I said step 1 is this. And why is that true? Well, reason 1 is distributed 1. And then I go on to step 2. And I could put whatever was on the right-hand side of my equation in step 1 down here and say, okay, well, A equals B, and B equals C, and C equals D, and so on. But one shortcut that you can take is you can just put another equals on here. So I can get from this left-hand equation to this right-hand equation by distributed 1. And then I can get from this step 1 on the right-hand side, to step 2 on the right-hand side. Well, that is because addition is commutative, right? And then I do my next step. Why? Because of addition, right? Do my next step. Why? Again, I swapped these guys. Addition is commutative. So we have the first half of our proof here. And we still need to add these other rules, and we need to add them from the bottom up. So step 5, and this is where people sometimes mess up. Step 5 is going from 30x plus 20 to 30x plus 8 plus 12, right? And when we were originally working on this, we said we start here and we go here, and how come we can do it? Because of addition. So what we need to do is we need to say, well, if I'm starting here and I'm going to here, how come I can do that? Again, because of addition, right? You just need to make sure that you put your reasons where they really belong, because you're sort of off by one when you're going back upwards, right? So my step 6 is I change it into this 8 plus 30x plus 12. here's where I change it into the 8 plus 30x plus 12. But the reason that I could go from here to here is the same reason I could go from up here down here. And that this was my because addition is commutative. So I put that there. And then my last step is I compute the right-hand side of my equation up here. It's hidden, but that's the right-hand side. And how do I get this? Well, I get this by going from here to here, which is the same reason I could go from here to here, distributed to, right? So I put that down there. So my proof is almost beautiful, but I'm not quite done. I mean, I will note that I started with this equation that's on the left. That's on the left-hand side here. I proved that it was equal to this equation on the right. That's down at the bottom of my proof, right? So far, so good. The last thing that you need to do is you need to add the initials QED. There should be a period there too, which stands for a Latin phrase, which I have just checked on our friend Google is quod erat demonstrandum, right? Which really means that's what I just demonstrated, right? That's what was to be demonstrated. So QED says, look, I did it and I'm done and I showed you. So you want to put this QED at the bottom of your proofs with another period there. Ideally, I won't take off points if you just write QED without the periods in there. I'm nitpicky, but I'm not quite that crazy. A lot of people remember QED. If you can't remember quod erat demonstrandum, you can also remember quite easily done, even if it wasn't so easy. So let's just look at our proof again. Here's our proof. Look how beautiful it is. We rewrote it, right? We rewrote it in super neat handwriting, and every single step is justified. So we have the step number over here, and we have the justification with the same number on the same line. It's just beautiful. If we're feeling really nice, we type it up, right? And the key to all of this is our proof is so beautiful. It makes it look easy. It makes it look like we could just do this in our sleep, right? Even if it takes us 3 days to figure out the proof, we copy it over. We make it look beautiful so that we can show we understand what a good proof really looks like. So there you go. That's it. We wrote a beautiful proof, just like you go through a maze, right? You might have to take some time to go from the front to the back to the front. You may hit some dead ends and go backwards a little bit. But eventually, once we figure it out, we redraw from scratch. And, or in the case of a proof, we rewrite our steps in order with justifications in order from scratch.